Okay, Cal PC, Unit 2, Day 5, assignment, office hours, page 450, 1 to 16 all. These are the questions. These are the answers, the even ones. Hopefully you check your odds in the back. You can pause it right now if you want to check them longer. I'm going to go ahead and keep going. So, let's see. First, 4 problems. Estimate the limit graphically and then use L'Hopital's rule to find the limit. So, number 1, limit as x approaches 2 of x minus 2 over x squared minus 4. So graphically, we're going to use a graphing calculator. And I'm going to also draw a sketch of it. So we're going to do parentheses x minus 2 divided by parentheses x squared minus 4. Window, I don't know, -5 to 5, -5 to 5. Now, just, some things to consider. We expect to maybe get a vertical asymptote, and looks like there's a hole there. But we're going to show that on our graph first. So as we approach 2, that's over here. So the graph looks like this, just a rough sketch. Vertical asymptote, x equals 2. Horizontal asymptote, y equals 0. And graph goes like this, and the graph goes like this. So we're saying as it approaches 2, so that's somewhere over here. So my graph, I'm just going to go trace. This is a very untechnical way of doing it, but as we get closer to x equals 2, y looks like it's getting closer from both sides to about 0.25. So I'm going to say I'm estimating that it's 1/4. Now, if you plug in 2, you get nothing. So that verifies there's a hole in the graph, but it looks like it's going to 1/4 on both sides. Now, algebraically, we're going to use L'Hopital's rule to justify this. Now, we've been doing holes, but we're going to go ahead, instead of using the hole, we're going to do, if we plug 2 in here, we get 0 over 0, which tells you it's the indeterminate form that we can use L'Hopital's rule on. So we're going to take the derivative of the top and the bottom and replug 2 in, and we get 1/4. So we're not using the whole approach anymore, at least for this assignment. In the future, it's kind of up to you. Sometimes L'Hopital's makes the most sense. Sometimes something else makes the most sense. Now, this is one that we've been doing algebraically, saying, okay, sine of something over the same thing equals 1, right? Multiply top and bottom by 5. Now, we're not going to do that this time, but that would give us an answer of 5, I think. But we're going to look at the graph real quick. So sine of 5x divided by x, and we'll go with the same window for right now. We'll decide if we want it, and we're approaching 0. So it goes up there. So we can do trace. As it gets close to 0, it looks like it's getting close to 5, and right at 0, it's nothing. There's a hole. So I'm going to draw a quick, so I'm saying I think it's 5 based off the graph, the sketch of the graph. It goes like this. Okay, so it looks like it has probably a horizontal asymptote, y equals 0, and this value right here, which appears to be a hole, is 5. Now, using L'Hopital's rule, first verify sine of 0 over 0 is 0 over 0. Okay, got it. You can't just use L'Hopital's rule whenever you want. You need to verify 0 of 0, infinity over infinity. And the derivative of this is going to be 5 cosine 5x. You do chain rule over 1. You plug 0 in. Cosine of 0 is 1. And we get 5. Okay, so that's what we're doing on these. Number 3, it's a limit as x approaches 2 of the square root of 2 plus x minus 2 over x minus 2. If we plug 0 in, we get square root of 4 is 2 minus 2 is 0 over 0. On the graph, let's do the graph. Square root of 2 plus x closed minus 2. We do need parentheses around the whole numerator. So second insert divided by parentheses x minus 2, close, graph. It's kind of weird. I think we get a better view of it. Maybe -3, -1 to, sorry, to 5, maybe -1 to 2. And we can make it even better. So it looks like looks like kind of like the bottom half of a sideways parabola. So we could probably do we get a little nicer. See that? It's kind of like looks like a sideways parabola, bottom half. Which squared functions are the inverse of parabola. So that's 1, and that's 2, and then +2. And the graph kind of looks like this. And it looks like, I don't know, maybe it's going towards, now it looks like it kind of dead ends here, which some functions do because of domain issues. And so if we're going to 2, let's see, trace, getting closer and closer to 2, and it looks like it's going to 0.25. So I'm going to guess that it's 1/4 based off the graph. And if we plug 2 in, just to verify, yep, looks like there's a hole there. So there's a hole, and it's going towards 1/4. Now, with L'Hopital's rule, it does go to 0 over 0. So L'Hopital's rule, we're going to want to think of this as a 1/2 power. 1/2, 2 plus x to the -1/2 times derivative of what's inside is 1. Derivative minus 2 is 0. Derivative bottom is 1. So if we plug 2 back into this, it's going to be 1 over 2 times the square root. 2 plus 2 is 4. And we get 1/4 using L'Hopital's rule. So verifies it. Number 4, limit as x goes to 1 of the cube root of x minus 1 over x minus 1. If you just plug 1 in, you get 0 over 0. I'm going to look at the graph. Window, no, y equals parentheses x to the parentheses 1/3. You got to put parentheses around that exponent. Minus 1, close parentheses on top, divided by parentheses x minus 1 on the bottom. Window, I'm just going to go ahead and go back to -5, -5 to 5 to see what that looks like. So there's the function. And then it does something weird right there. Maybe we could get a little better view. Maybe just go -1 to 2 in the y direction. Maybe not go as far in the x. It's kind of interesting looking graph. So it's doing something strange right there. Now, think about it. When x equals 1, something definitely is happening here. I mean, we could do second calculate x equals 1, and there's nothing there. There's a hole. When x equals 0, the graph should be fine. So it looks like as we approach x equals 1, it looks like it's going to like 1/3. So I'm going to draw a sketch of this real quick. And the graph kind of goes like this, and then it goes like this. And at 1, there's a hole, and it looks like it's going to 1/3. So we're going to say right now that we think the answer is 1/3. And then we're going to use L'Hopital's rule, which has to take the derivative of the top and bottom. So that's going to be x to the 1/3 as power. 1/3 x to the -2/3 over 1. If we plug 1 into that, that's 1 over 3. 1 to the 2/3. 1 to the 2/3 is 1, so we get 1/3. Same answer. Okay. Okay. So the next group of problems, 5 through 8, says apply the stronger form of L'Hopital's rule to find limit, which means that we're probably going to have to use L'Hopital's rule more than once. So And we're not trying to do it graphically this time, so these should be a little quicker. Plug 0 in, we get 0, 0, cosine 0 is 1, 1 minus 1 is, okay, so we can do L'Hopital's rule. I want to see that verification. Now, that's actually the laziest way of doing it. On first response, that's not good enough. A derivative top is going to be positive sine x because derivative cosine is negative sine. Bottom is 2x. If you plug 0 in again, sine of 0 is 0 over 2 times 0 is 0, which means we can do L'Hopital's rule again. And derivative top is going to be cosine x. Derivative bottom is 2. Cosine of 0 is 1, and we get 1/2. So that's the stronger form. It just means that we're having to do it more than once. Okay, number 6. Theta going to pi over 2 of 1 minus sine theta over 1 plus cosine 2 theta. If you plug pi over 2 in, sine of pi over 2 is 1, 1 minus 1 is 0. Cosine of pi is negative 1, 1 plus negative 1 is 0. So we can do L'Hopital's rule. And derivative top is going to be negative cosine. Derivative bottom is going to be negative 2 sine 2 theta. Plug pi over 2 in. Cosine of pi over 2 is 0. Sine of pi is 0. So I'm going to do it again. The top is going to be positive sine 2 theta, or positive sine theta. The bottom is going to be negative 4 cosine 2 theta. I got to do chain rule. Now when we plug pi over 2 in this time, that's 1. Cosine pi is negative 1, so it's going to be positive 4 for the bottom. Okay, 7, limit as t goes to 0 of cosine t minus 1 over e to the t minus 1. If you plug 0 in, cosine 0 is 1 minus 1 is 0. E to the 0 is 1 minus 0 minus 1 is 0. So we're going to do L'Hopital's rule. Cosine is going to be negative sine. And derivative e to the t is e to the t minus derivative of minus t is minus 1. Derivative of minus 1s are 0. Sine of 0 is 0 over e to the t is 0. E to the 0 is 1 minus 1 is 0. So we're going to do it again. We're going to get negative cosine t on the top and e to the t on the bottom. And cosine of 0 is 1, so it's going to be negative 1 over e to the 0 is 1 is negative 1 for your final answer. Okay. Number 8, I'm going to go ahead and try and sneak it in here, as these are the same kinds of problems. I'll scoot my paper over. So if we plug 2 in, we get 4 minus 8 is negative 4 plus 4 is 0. 8 minus 24 is negative 16 plus 16 is 0. So we're going to do L'Hopital's rule. Derivative of the top is going to be 2x minus 4. Derivative of the bottom is going to be 3x squared minus 12. If we plug 2 in there, we get 4 minus 4 is 0. 3 times 4 is 12 minus 12 is 0. So we're going to do it again. And so we're going to get 2 over 6x. Now when we plug 2 in, we get 2 over 12, which is 1/6. So stronger form of L'Hopital's rule. All right. On the back, next problem say, exercise 9 through 12, use L'Hopital's rule to evaluate the one-side limits. Support your answer graphically. So we're going to find the answer with L'Hopital's first. It's kind of like 1 through 4, but backwards. We're going to find the answer and then use a graph to support it. So there's multiple parts here. Number 9, limit as x approaches 0 superscript negative. Sine of 4x over sine of 2x. If we plug approaching 0 from the left side, which means that we're going to get 0 over 0. And then we're going to do L'Hopital's rule. And we're approaching 0 from the left. And the derivative of the top is going to be 4 cosine 4 theta. And the bottom is going to be 2 cosine 2 theta. And as we approach cosine of 0 from the left, it's approaching positive 1. So we're getting positive 4 over 2, which is 2. And then part B, we're going to do the same thing, but from the right-hand side. So probably see some similar things happen. We get 0 over 0. Now we're here, it's like really negative 0 over negative 0 because you're pushing from left. This is like positive 0 over positive 0, but either case is indeterminate. And then L'Hopital's rule, derivative of the top, 4 cosine 4x, derivative of the bottom, 2 cosine 2x. We plug 0 into that. Either side, cosine of 0 is approaching positive 1, so it's going to be 4 over 2, which is 2. So the two one-sided limits agree with each other. Now on a graph, we're going to support our answer graphically. So we'll put this in sine of 4x divided by sine of 2x. Window, I don't know, negative 5 to 5. Now this is negative 5 to 5. We'll just try that. Okay, so here's the graph. And it kind of looks like a regular sort of cosine curve, actually, right? And so we're going to do trace, and as we get closer to 0 on both sides, it does look like it's approaching 2. So the graph looks like that. And at if we do second calculate value at x equals 0, it is nothing. There's a hole. So I think there's a hole here inside 2, so that from both sides, it does appear to be approaching that. So that's our graph to support our answer. 10, part A, limit as x goes to 0 infinity of sine x over x cubed. If we plug 0 in, we're approaching 0 from the left, so this is approaching 0, but from the negative side, this is approaching 0 from the negative side, but that's indeterminate. So then we can do L'Hopital's rule, and we get cosine x over 3x squared. Now when we approach 0 on this, we're going to get 1 over positive 0 because it gets squared, which is going to go to positive infinity. It's going to blow up to positive infinity. Then part B, we're going to do the same thing from the other side. 0 plus, actually, yeah, this is actually problem 11. I'll just go ahead and keep finishing problem 11. I skipped not 10, I'll come back to it. So sine x over x cubed, it's going to equal positive 0 over positive 0 in indeterminate form. Allows us to do L'Hopital's rule, derivative of the top, derivative of the bottom. We're approaching, now the plus makes a difference here because this one's going to positive. This is approaching 0 from the right side, which is going to be 1. This is approaching 0 from the right side, so that's going to be a positive 0. So that's going to be positive infinity also. So the graph, we're probably looking at some kind of vertical asymptote. So I'm going to go and graph this. This is sine x divided by x to the third graph. And boom, boom, looks like a vertical asymptote there. So if you go trace and we get closer and closer, at 0, there's nothing, right? It's a vertical asymptote, but you'll see the values are starting to blow up as we get close to 0 from both sides. And they're both going positive, so that makes sense with the results we got algebraically from L'Hopital's rule. The graph looks like this. It's going to infinity on both sides. It's going to positive infinity on both sides. It looks like there's a vertical asymptote. Okay, now back to problem 10, which I accidentally skipped. Part A was the limit as x goes to 0 negative of tangent x over x. And that's going to be, tangent sine over cosine, right? So sine of 0 is 0 over cosine of 0 is 1. So that's going to be 0 over 0. From the left side, It's going to be negative. So we're going to do L'Hopital's rule, limit as x approaches 0 minus. Derivative tangent is secant squared over 1. Now secant squared is 1 over cosine x. So now we're approaching 0 from the left side. Cosine of 0 is 1. It's going to be 1 over 1 is 1. Okay. And then part B, limit as x approaches 0 from the right side of tangent x over x is going to give us, tangent is sine over cosine. Cosine of 0 is 0. Cosine of 0 is 1. Push on right is going to be positive 0 over positive 0. We do L'Hopital's rule. And derivative tangent is secant squared x over 1. Secant is 1 over cosine squared. Right? So cosine of 0 from the right side is 1. Squared is 1. 1 over 1 is 1. Let's see if we can fit 12 on here too. So the graph is going to be tangent x over x. And so we're getting these vertical asymptotes and stuff. This is what the graph looks like. And we're concerned about when it's getting close to 0. But it looks like around 1.5 vertical asymptote, negative 1.5 vertical asymptote. It looks like it goes like this, right? And then it's kind of going like this. And over here it's going like this. And so as we approach 0 from both sides, looks like it's going to the same point. Trace, looks like it's going to 1, right? And at 0, it seems like there's a hole. So it looks like it's going to 1. So that makes sense with what we got. 12, last kind of problem like these. Let's see, it's the limit as x approaches 0 minus of a tangent x over x squared. So sine over cosine, it's going to be 0 over 1 is 0 from left-hand side over the positive. So that might, we'll see what happens with that. So we're going to do L'Hopital's rule. And derivative top is going to be secant squared x over 2x. Now that's going to be 1 over cosine squared x. That's going to be 1 over negative 0. That's going to go negative infinity, which, by the way, that right there indicated that a negative or a positive, we should get a negative answer. So it looks like there's a vertical asymptote there. Now we're going to do the same thing, but for the right side. And so sine x over cosine x, 0 over 1, that's going to be positive 0 over positive 0. So we expect to get a positive answer. I always do that. I always keep track of, is it something small positive or something small negative? It's not quite 0. It's going towards 0. So that's going to be secant squared over 2x. That's 1 over cosine squared x. That's going to be positive 1 over positive 0. That's going to go to positive infinity. So the graph of this is tangent x over x squared. Graph it. Nope, doesn't like that. I said I should have just said square. I did caret squared, caret 2. Graph it. Looks like some vertical asymptotes there. So a quick sketch of this, and especially where we're going to 0. But it looks like around 1.5, there's a vertical asymptote. Negative 1.5, there's a vertical asymptote. So the graph's kind of going like this, and here it's going like this. So it looks like there's another vertical asymptote here, and it's going like this, and then it's going like that. And so as we approach 0 from the left, it's going to positive infinity. As we approach 0 from the left, from the right, it's positive. From the left, it's going to negative infinity. So that backs up our answer. Okay, and then Okay, problems 13 to 16 say identify the indeterminate form and evaluate the limit using L'Hopital's rule. Support your answer graphically. So 13 is the limit as x goes to pi of cosecant x over 1 plus cotangent x. And cosecant is 1 over sine, so sine of pi is 0, so it's going to be like an infinity over cotangent is cosine over sine, so that's going to be like an infinity. So that's that indeterminate form. So then we could do L'Hopital's rule, and derivative of cosecant is derivative of secant and secant tan, so this is cosecant cotan negative. Derivative of cotangent is cosecant squared. We could clean this up and cotangent is 1 over tangent, so it's cosine over sine, and cosecant's 1 over sine, so the sines cancel, and so this should be the same thing as x goes to pi of cosine, and that would be -1. Graphically, we have to type this in 1 divided by sine divided by parentheses 1 plus parentheses 1 divided by, or sorry, yeah, we can do 1 over tangent, close, 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 graph it. So pi is about 3 point whatever, so pi is right around there. So we're going to see what it does. So graphically, trace, if we try and get over here close to pi, 3.14. 3.14 looks like it's around -1, right? So we could draw a quick sketch of that. And so right around here on pi, it's around -1. Now I don't think it's a whole necessarily, so I can calculate. Well, we can try it. Value pi, I guess it's a whole. So that'd be around -1. And so the graph kind of looks like this. And there we go. Okay, 14. Limit as x approaches pi over 2 of 1 plus secant x over tangent x is going to be secant is 1 over cosine, tangent is sine over cosine, and we get cosine of pi over 2 is 0, so that's going to be infinity over infinity. Now, one possibility is we can maybe just simplify this without doing L'Hopital's rule, and it might work out nice, but I guess we are trying to do L'Hopital's rule, so I guess we're going to try and do L'Hopital's rule. Derivative secant is secant tan. Derivative tangent is secant squared. So the secants can clean up. Tangent is sine over cosine, and secant is 1 over cosine. So then that gives you, as x approaches pi over 2 of sine, which is +1. So on a graph, we can take a quick look at that. We would do parentheses 1 plus parentheses 1 divided by cosine x, close, close, divided by tangent x, close, get rid of all the rest, and then we could do graph, get some vertical asymptotes. And so we're approaching pi over 2, which is about 1.6, 1.5, which is right around there. So looks like vertical asymptote is around pi and negative pi. And the graph kind of goes like this and like this. And so as we approach pi over 2, right around there, second calc. Well, I mean, we could just try this first. Pi over 2, nothing. There's a hole. Trace. Looks like it's going towards 2, right? So there's a hole, and it's going towards 2 from both sides, so it should be 2. 15. Limit as x approaches infinity of natural log of x plus 1 over log base 2 of x. And now as you go to infinity, natural log graphs go to infinity. So this is infinity over infinity. So then we do L'Hopital's rule. 1 over what's inside times root of what's inside. 1 over what's inside. Now if it's a log base, it's going to have an extra natural log of the base in the denominator. And then we might want to go ahead and rewrite this like this. And then it's still going to be infinity over infinity. So I guess we could do it again. And the derivative of the top is going to be just natural log of 2. The derivative of the bottom is going to be 1. So the answer should be natural log of 2, which on my calculator, just to help me compare it to what I get, is 0.693. So the graph is natural log of x plus 1. Now divided by, now logs with other bases, we could use the change of base formula to change the log base 10 of x over log base 10 of the previous. So that would be log of x closed divided by log of 2 closed. So that should give us the same thing as log base 2 of x. Okay, graph it. So we're looking at what happens at 2 right there. So this kind of looks like a rational function. And I mean, it looks like there's like a vertical asymptote around -1, maybe. It's not super important to us because we're not looking there, but we're looking at 2. Sorry, rational vertical asymptote x equals +1. So we could do the whole second calc value x equals 2. Oh, it actually just gives us the answer. Actually, sorry, we're going to infinity. So it's got to look like, well, what's this graph going to as we go to infinity? And so I guess it would help to do the window maybe bigger in the x direction, say 20. And just graph that, just to get an idea, like, do we kind of get some, it looks like it's leveling out at some value. So, I mean, we could say second, yeah. So I'm on trace and it's going slowly, slowly getting closer to what looks like 6.9. So that seems like reasonable. Like there's a vertical asymptote y equals 0.693 or something close to that. It's not perfect, but I think it helps us feel good about our answer. 16 is the limit as x goes to infinity of 5x squared minus 3x over 7x squared plus 1. Now, we've looked at ways of answering this with dominant terms, things like that, but we're going to use L'Hopital's rule. We're going to show the indeterminate form, infinity over infinity, which is something I always want you to show, but they're telling you explicitly to show it. And that tells you that we can do L'Hopital's rule. So it's going to be 10x minus 3 over 14x, which is going to also give us infinity over infinity. Now, we know right now these are the dominant terms. The answer is going to be 5/7, but we're using L'Hopital's rule, which is definitely not faster this time, to get the answer 5/7. Now, the graph of this is going to be a rational graph. Y equals parentheses 5x squared minus 3x closed divided by parentheses 7x squared plus 1 close window, I'm just going to say -5 to 5, -5 to 5 right now. And so kind of does something kind of funny there. I guess we could change our window to see a little better. Maybe -1 to 1 for the y value. So there's this graph, kind of goes up a little bit, and then it dips. So it kind of goes like that. And it kind of goes like that. And so then as we approach infinity, what's happening over here? So I think the window would be better if we made the x go further and see if it's approaching some kind of horizontal asymptote. We could do second calc, say 19, enter, and it's going towards what looks like 0.69. And what's 5 divided by 7? 0.71. Okay, 714. So back to the graph. I mean, maybe we make the window even bigger, 40, graph it, and then it's going up, right? So if I put calc 39, it looks like it's going up. So it looks like it might get close to that. So that seems like a reasonable answer. So there you go. Lots of practice with L'Hopital's rule. Looking at it graphically first, verifying it with L'Hopital's rule, doing it with L'Hopital's rule first, verifying it with graphs. So lots of derivatives.